Today I will take you on a small tour of partial differentiation. Under certain continuity conditions, we can find the partial derivatives of a function. But what is basically required is that we must have a function of at least two independent variables, two or more. Suppose we have a function z is equal to f of xy, where x and y are the independent variables. We say z is a dependent variable. Now, how does one visualize this? We can visualize a function like this as a surface in 3D space. Similarly, when we have z as a function of more than two variables, then we are in a space consisting of let us say 4 dimensions or 5 dimensions or n dimensions, depending upon the number of independent variables. Now, what is the notation? Zx stands for dou z by dou x, zy stands for dou z by dou y, zxx stands for dou square z by dou x squared, zyy stands for dou square z by dou y squared, zxy stands for dou square z by dou y dou x. Now, these are called the first and second order partial derivatives of z. Now, at the engineering level, partial differentiation is generally studied for the purpose of function optimization, that is, in studying the maximum and minimum values of a function. For this theory, it is sufficient to deal up to the second order partial derivatives. Now, what does this first order partial derivatives mean? And how does the second order partial derivatives help us in optimization? One of the very important vectors that we see in field theory is the gradient vector. The gradient vector is generally denoted by del f. And this is nothing but fx, fy transpose. So, this vector, which consists of the first order partial derivatives, is very important in determining the critical points of a function, about which we will discuss later on. Similarly, when you take the second order partial derivatives, we can construct a matrix which is called, which is denoted by H, and its structure is something like this. When we have two independent variables, when we have three independent variables, the matrix H obviously will be of order 3 by 3. Now, this matrix H is known as the Hessian matrix. As we proceed through the syllabus, let us see how the gradient vector and Hessian matrix are very critical in understanding the maxima minima problem. But first, I would like to show you a few illustrations on the first order partial derivatives and how a very small but very nice theorem known as the Euler's theorem can enable us to do some fast computations, and then the concept of total derivative, then the concept of Jacobians, and how one handles implicit functions to find out the derivatives. This is all we would like to see in the next 1 hour or so. So, let us start a few illustrations. Friends, you are all aware that when we find out dou f by dou x and dou f by dou y, we have to be very watchful about which variable is kept constant. For example, when we find out dou f by dou x, we treat the variable y as constant. When we find dou f by dou y, we keep the variable x constant. However, all the rules of differentiation will remain the same. The so-called product rule or the quotient rule, all these things can be effectively used, but with the special care that we must freeze certain variables as constant. Now, my first problem that I am going to show is given z is equal to tan inverse y by x. What is zx? That is, what is dou z by dou x? So zx is equal to 1 upon 1 plus y by x whole squared into dou by dou x of y by x. So this is the differentiation of the tan inverse function. So if you simplify, you get this, and with respect to x, y is a constant, so you can pull it out, y dou by dou x of 1 by x. So x squared by x squared plus y squared into y into minus 1 by x squared. So this gives us minus y by x squared plus y squared. So this is how you can maintain all the rules of differentiation exactly the same while keeping an appropriate variable constant. In this case, differentiation with respect to x is going on, therefore the variable y is treated as constant. So the correct option for this problem is A. Partial differentiation question number 2. If u is equal to e power x plus y by e power x plus e power y, then to compute ux plus uy. Applying the quotient rule of differentiation, and you will find that e power 2x plus y will get cancelled, leaving behind e power x plus 2y by e power x plus e power y whole squared. Similarly, uy would be e power 2x plus y by e power x plus e power y whole squared. So let us take the sum of these two. Ux plus uy would be e power x plus y will be a common factor, e power y plus e power x divided by e power x plus e power y whole squared, leaving behind e power x plus y by e power x plus e power y, and this is nothing but the given function u itself. Therefore, the correct option for this problem is D. We have a third question in which w is equal to y by z plus z by x. The requirement is the output of x wx plus y wy plus z wz. Now for students who have done partial differentiation early on, this can be done directly or by using this famous Euler's theorem. I will give you both the things, but first let me show you the direct way of doing this problem. Now let us start with wx. Wx is equal to, now the x is found in this area, therefore this is a constant, derivative of a constant is 0, z is a constant, differentiation of 1 by x is minus 1 by x squared. Then we go to wy. Wy, this will produce 1 by z plus 0 because there is no y. Wz is equal to, z is present in both the places, so minus y by z squared plus 1 by x. Now let's find out xwx plus ywy plus ZWZ. So this is x into minus z by x squared plus y into 1 by z plus z into minus y by z squared plus 1 by x. So let's simplify. Minus z by x plus y by z minus y by z plus z by x. You can find that the answer is 0 after all the calculations, and the correct answer is A. This is one of the ways by which we can do this, but as I told you, we have the benefit of the Euler's theorem, about which I'll briefly talk, and then apply the Euler's theorem for this particular problem. So let us see what that solution is. This is another approach to the same problem. Now what does the Euler's theorem say? If W let us say a function of xyz is homogeneous of degree n, then xwx plus ywy. Now this is a very strong statement. What is required is that the function should be homogeneous. Now let us see, in this particular case that we are discussing, what is the degree of this function. Now because this is an algebraic function, the degree can be easily assessed. Degree of y is 1, degree of z is 1. So the degree of y by z will be 1 minus 1, 0. Similarly, the degree of the second term is also 0. Therefore, W is homogeneous of degree 0. W in this case is homogeneous of degree n is equal to 0. So when you put n is equal to 0 here, you get xwx plus ywy plus zwz is equal to 0 into w is equal to 0. That is how you get the same answer as before. But please observe, we practically did no differentiation and we are able to predict the answer straight away from the Euler's theorem. But if w were not homogeneous, then we cannot say the answer would be n into w. Something else would be issued out, for which either we must go by direct differentiation or look for other patterns in the function. Let's go to the next problem. The problem is, if u is equal to x squared plus y squared plus z squared whole power minus half, what is the output of ux whole squared plus uy whole squared plus uz whole squared? This is a plain differentiation problem, but handling the function and its derivatives can make the entire exercise very, very easy. So let me show you the computation of ux first. Ux is equal to differentiation of this power function is minus half x squared plus y squared plus z squared power minus 3 by 2 into the derivative of x squared is 2x. So this can be written as minus x, and this in terms of u will be u cube. Similarly, uy will be minus y u cube and uz is equal to minus z u cube. So that way we have compressed the entire thing in simple terms. Now, let us take this expression. Therefore, ux squared plus uy squared plus uz squared is equal to the sum of the squares of these things will give us u power 6 into x squared plus y squared plus z squared. But one can observe from the given function that u squared is equal to x squared plus y squared plus z squared whole inverse. Therefore, x squared plus y squared plus z squared must be the reciprocal of u squared. So, this is u power 6 into 1 by u squared. So, u power 4 is the output, and you can observe the correct answer is D. So, this is a plain differentiation problem, but handling the simplification makes the problem very, very easy. Let's go to the next question. We are given z is equal to x squared plus 2y squared, and further x is equal to r cos theta, y is equal to r sin theta. The problem is to find dou z by dou theta with r as constant. Now let us observe this notation. Dou z by dou theta with a suffix r means keeping r constant, what would be dou z by dou theta? This means we'll have to transform the equation z in terms of the indicated variables r and theta. So for that, you substitute x is equal to r cos theta and y is equal to r sin theta here, then z would transform into a function of r and theta. So let me show you that. So z is equal to x squared would be r square cos square theta, 2y square would be 2r square sin square theta. So now let us find out dou z by dou theta with r as constant. So r square into, we differentiate cos square theta. This is 2 cos theta into minus sin theta plus 2r square into, differentiate sin square theta, you get 2 sin theta into cos theta. Please observe that 2 sin theta cos theta is a common factor, and that is nothing but sin 2 theta. So we'll have minus r square sin 2 theta plus 2r square sin 2 theta. This will be nothing but r square sin 2 theta, and the correct option is B. There are varieties of questions which can be designed. For example, he could say dou z by dou theta, dou z by dou r with theta as constant, or dou z by dou x with theta constant. So all that would mean is you observe what are the indicated variables and accordingly design z and then perform the differentiation. So let's go to the next question. Okay, first let us look at this part, dou u by dou x. Observe that u is distributed in two places. So we'll have to first solve these two equations for u in terms of x and y. Second part is straightforward because x is already present here. So for the second part of the calculation, this equation is enough. But for the first part of the solution, we have to first derive an expression for u. So if you add the two expressions, x squared plus y squared is equal to 2au. So u is equal to x squared plus y squared by 2a. So now we can find this derivative. Dou u by dou x with y as constant is 2x plus 0 by 2a or x by a. Now for this part of the calculation, let us pick up this equation. Differentiate this equation with respect to u. So 2x dou x by dou u is equal to a plus 0. Therefore, dou x by dou u is equal to a by 2x. This is with respect to u, therefore v is constant. Therefore, dou u by dou x with y constant into dou x by dou u with v constant is equal to the product of x by a and a by 2x. So you can see that the output is half. So C is the correct option for this problem. So these can be very small problems but can confuse one type of students who are not sure about manipulating equations. Let's go to the next question. Okay friends, in this question, let us find out dou u by dou x with y constant and dou x by dou u with v constant. It's almost like the previous problem. Now dou u by dou x with y constant means the first equation is sufficient. So dou u by dou x keeping y constant will be L. But when it comes to the second equation, dou x by dou u with v constant, we have to solve these two equations for x. So we'll have to eliminate y. So let me show you that. So we can write the first equation as Lx plus my minus u is equal to 0, mx minus ly minus v is equal to 0. Let us solve this equation for x. So one simple way is you multiply this equation with L and this with m and then add. So you will get L square plus m squared into x minus Lu minus mv is equal to 0. So x is equal to Lu plus mv by L square plus m squared. Once this is available, we can find out dou x by dou u. So dou x by dou u with v as constant, the denominator is obviously constant, so you will get L by L square plus m square. So now we have to take the product of this and this. So the product of these two, therefore dou u by dou x with y constant, dou x by dou u with v constant is a product of these two, which is L squared by L square plus m square. So this makes option B the correct option. So not much except for manipulating the two equations to get x in terms of u and v. So no challenge in this particular problem. Let's go to the next question. Given u is equal to sine inverse x minus y, further x is equal to 3t, y is equal to 4t cube, what is the output of du by dt? I will not introduce the concept of total differentiation immediately, but I will do it directly because that is much easier for this context. So what you can do is, you can substitute x is equal to 3t, y is equal to 4t cube and then proceed to differentiate u with respect to t. However, you will find that the simplification part will be very elaborate. So I will change my parameter t in this problem to suit the context. So what we do is, let t is equal to sine theta. So there is nothing but a change of parameter. So then u would become sine inverse of 3 sine theta minus 4 sine cube theta. This is sine inverse of sine 3 theta, which is 3 theta. But you can see theta is sine inverse t. So what we have achieved in this problem is to express u in terms of the parameter t in a very simple way. So du by dt would be 3 by square root of 1 minus t square. So the correct option is D. As I told you, there is another option available before the student, that is to use the concept of total differentiation. but I have a small set of problems where I am going to use that concept. Definitely not for this particular question. Let's go to the next problem. The question is, if v is equal to 1 minus 2xy plus y square whole power minus half, to compute x vx minus y vy. To most students, this function may look just an ordinary function, but for students who are deep into special functions, they will know that this function is called the generating function of Legendre polynomials. All of us know Legendre polynomials are very special functions for the engineering student. Anyway, beside that, let us just plan how to solve this problem. Vx is equal to minus half into 1 minus 2xy plus y squared whole power minus 3 by 2 into the differentiation of this term with respect to x. So you get minus 2y. So after simplification, you get y into, now this is the cube of this part, so it is v cube. Now let us find out vy. Same procedure, minus half into 1 minus 2xy plus y square whole power minus 3 by 2 into, now these are the two terms involving y. Differentiate with respect to y partially and you get minus 2x plus 2y. So you can simplify a little bit and get x minus y into u cube. Now we require x vx minus y vy. So x vx minus y vy is equal to x times this, so you'll get xy v cube minus y times this, so you get xy minus y squared v cube. So you can find xy v cube minus xy v cube cancelling off, and you are left with y square v cube. So you get a very simple result in terms of v. This is considered a very important result in Legendre polynomial theory, but however the scope of this problem is only this much. The correct answer to this question is C. Let's go to the next question. Dear friends, I would like to now discuss the concept of total derivative, which is one of the critical topics in partial differentiation. Generally speaking, there are about three important areas in partial differentiation. One is the slightly simpler Euler's theorem. The next thing of great importance is the total derivative. And the third one is the concept of Jacobians. So I will be discussing all of them now in detail, but first let us look at the total derivative concept. Now let us see two broad cases. In one case, let us say u is a function of x and y, where x and y are functions of a parameter called t. Then the total derivative of u with respect to t is dou u by dou x into dx by dt plus dou u by dou y into dy by dt. A slightly bigger picture is when you have u as a function of x, y, z, where x, y and z are functions of more than one parameter. In this case, s and t are the two parameters. So you will have two total derivatives, the total derivative of u with respect to s and the total derivative of u with respect to t. As you can easily see from the diagram, dou u by dou x into dou x by dou s plus dou u by dou y into dou y by dou s plus dou u by dou z into dou z by dou s. Similarly, with respect to t, dou u by dou x into dou x by dou t plus dou u by dou y into dou y by dou t plus dou u by dou z into dou z by dou t. So with these principles in mind, let us do a few problems. One has to identify how many parameters are there in the system and accordingly proceed. The slightly tougher problems will be problems where we have to find out higher order partial derivatives with respect to the parameters. But given the scope of these exams, we will confine ourselves to the total derivatives of the parameters of the first order only. So let's begin a problem series. Friends, in this question, we are given u as a function of three variables x, y, z. X, y and z are all functions of a single parameter t. Therefore, we can find out du by dt, and the requirement is what is the value of this total derivative at the specific value of t is equal to 2. So let's first set up our formula. Du by dt is equal to dou u by dou x into dx by dt plus dou u by dou y into dy by dt plus dou u by dou z into dz by dt. Okay, dou u by dou x will be 3x squared y e power z. Dou u by dou y will be x cube e power z, and dou u by dou z will be x cube y e power z. Dx by dt will be 1, dy by dt will be 2t, and dz by dt will be 1 by t. So the basic differentiation part is over. Now we want at t is equal to 2 the output of all these things. So let's do some side calculations. At t is equal to 2, we will have 3 into x square. X square is t squared. So therefore 3 into 4 12, 12 into t squared. So you can actually see 3 into 4 into y is t squared, so that becomes 4, and e power z. E power z is nothing but e power log 2, that is nothing but 2. That is because z is equal to log t and t is equal to 2. So e power z is 2 plus x cube is 8, e power z is 2, 2 into t, 2 into 2 4 plus x cube is 8, y is t square, that is 4 into 2 into 1 by 2. Okay, so we can make simplifications. 16 into 6 is 96, then 16 fours are 64 plus 32. So let's add up these quantities. 96 plus 64 is 160 plus 32 is 192. So the correct option for this problem is C. So this is a simple problem where u depends upon only one parameter. So the correct option for this problem is C, and this is how one should approach the problem. Another way of doing this problem is directly feed x, y, z values into the function, make it a function of a single variable, and avoid the total derivative concept completely. It is left to the student, but one has to be careful not to complicate the matters. Whichever is the easiest path, that may be adopted. Let's go to the next question. U is equal to x square minus y squared. X is equal to 2r minus 3s plus 4. Y is equal to minus r plus 8s minus 5 and we want dou u by dou r. Now please observe, u is a function of x and y. X and y are both functions of r and s. So this is based on two parameters. So you can draw a simple tree diagram. U as a function of x and y. X and y are functions of r and s. So we want dou u by dou r. So let's first set up the formula. Dou u by dou r is equal to dou u by dou x into dou x by dou r plus dou u by dou y into dou y by dou r. Dou u by dou x is 2x, dou u by dou r is 2, dou u by dou y is minus 2y, dou y by dou r is 1. So we'll have 4x minus 2y, which is 2 into 2x minus y. There are two things you can do. You can either now we have minus r here, therefore you will have a minus 1 here, so it will become plus plus. So you can leave it at this. Given the options, this is option number B, but one can even express the answer in terms of r and s, but that has to be decided by the student by looking at the context. So we can stop it here because this option appears in the list. So let's go to the next problem. In this question, which is again based on the total derivative concept, one can observe that x and y are both functions of u and v. But from the question, we can easily see that z is the dependent variable. So we can draw a tree diagram accordingly. Z is a function of x and y, where x and y are functions of u and v. So let's find out zu and zv. Zu is equal to dou z by dou x into dou x by dou u plus dou z by dou y into dou y by dou u. The relation between z and x is unknown, so we retain that. Dou x by dou u is e power u plus 0 of course, plus dou z by dou y into dou y by dou u is minus e power minus u. Similarly, let's find zv. Again you set up the formula dou z by dou x into dou x by dou v plus dou z by dou y into dou y by dou v. So dou z by dou x by dou v will be minus e power minus v. This is a constant. So let's write minus e power minus v plus dou z by dou y. Dou y by dou v is minus e power v. So with this, the raw form of zu and zv are available. So we'll just subtract these two equations and see what the output comes out as. Zu minus zv is equal to this minus this. So we can take dou z by dou x common. And you're left with e power u minus of minus plus e power minus v minus dou z by dou y. So we take minus common from these two and you will have e power minus u minus e power v. But you can easily see e power u plus e power minus v is x and e power minus u minus e power v is y. So this is reduced to x zx minus y zy. So you can see from the options that D is the correct answer. So this is another problem where a tree diagram can help you to write the total derivative formulas correctly, and the rest is left to carefully doing the differentiation. Let's go to the next problem. In question number 13, you have v is equal to f of 2x minus 3y, 3y minus 4z, 4z minus 2x, and 6 times vx plus 4 times vy plus k times vz is equal to 0 is given. The requirement is to find the unknown value of k here. This is a very nice problem based on the total derivative concept. First, what we do is we make substitutions for 2x minus 3y, 3y minus 4z, 4z minus 2x. So, let us write v is equal to a function of, let us say, alpha, beta, gamma, where alpha is 2x minus 3y, beta is equal to 3y minus 4z, gamma is equal to 4z minus 2x. So, from this, what is that one can observe? We can find that v is a function of alpha, beta, gamma. Alpha is a function of x and y. Beta is a function of y and z. Gamma is a function of x and z. From these relations, we can draw the diagram. Now, let's find out Vx. So, what is Vx equal to? X is present here and here. So, it is connected to alpha and gamma. So, we can say it is V alpha into alpha x plus V gamma into gamma x. This is nothing but V alpha into alpha with respect to x is 2, gamma with respect to x is minus 2. So, this is nothing but 2 times V alpha minus V gamma. So, when we actually enter this equation, we will just use that for Vx. Vy is equal to, y is present under alpha and beta. So, V alpha into alpha y plus V beta into beta y. So, this is V alpha into alpha with respect to y is minus 3 plus beta with respect to y is 3. So, we will have 3 common minus V alpha plus V beta. Finally, Vz is equal to, now z is traced under beta and gamma. So, therefore, V beta into beta z plus V gamma into gamma z. So, this is V beta into beta with respect to z minus 4, gamma with respect to z is 4. So, this is 4 times V gamma minus V beta. Now, you will have to just enter these things in this equation. So, when you substitute 12 V alpha minus V gamma, then 4 times this. So, this will be plus 12 times minus V alpha plus V beta. Now comes a problem. 4 Vz, that becomes 4k times V gamma minus V beta, but this should be equal to 0 as given. So, one can easily observe if the output has to become 0, then 4k should also be equal to 12, otherwise it is not possible. So, 4k is equal to 12 implies k is equal to 3. So, you can check the options and find D is the correct answer. So, this is a nice problem where total derivative is involved with 3 parameters, and then it is a simple question of manipulation. You must observe that in order that this becomes 0, all of them must mutually cancel. For that, this coefficient must also be equal to 12. So, that is how we get k is equal to 3. Let us go to the next question. Okay friends, in the next part, we will concentrate on 3 problems based on the Euler's theorem. You know, Euler's theorem is a theorem meant for homogeneous functions, and there are some direct results which are possible. So for your quick reference, I'll explain Euler's theorem and its extension. One is, if U is homogeneous in x and y of degree n, xux plus yuy is equal to nu, x squared uxx plus 2xy uxy plus y square uyy is equal to n minus 1 into u. This is when U is homogeneous. We have another result which says, if f of u is homogeneous in x and y of degree n, xux plus yuy is equal to n f of u by f dash u, x squared uxx plus 2xy uxy plus y square uyy is equal to g of u into g dash u minus 1, where g of u itself is n f of u by f dash u. So these are the two extensions of the Euler's theorem, and let us see some problems based on these very important results. In question number 14, u is equal to y square e power y by x plus x squared tan inverse x by y. The problem is to find x square uxx plus 2xy uxy plus y square uyy. Now please observe that there is a pattern in this and there is a pattern in this. Let us write it as a small note. U will be homogeneous of degree n if U is identically equal to x to the power of n into a function of y by x, or U is equal to y to the power of n into a function of x by y. Now these are compact representations of homogeneous functions. Now observe, in this case, y square e power y by x, of course we can also have a function of y by x here and a function of x by y here. So you can easily recognize that this is homogeneous, this is also homogeneous, both of them are of degree 2. So we can make a statement: U is homogeneous of degree 2. Now accordingly, we have a direct application of Euler's theorem which says the output has to be n into n minus 1 into u, where n is 2. 2 into 2 minus 1 into u, so it is 2u. So you can easily find the correct option is B. I don't think students will fall into the trap of actually performing differentiation. No. Look at the Euler's pattern here. So immediately apply the Euler's theorem. So this is the easiest way by which we can solve this result. So let's go to the next question. In question number 15, f is given as the log of x power 4 plus y power 4 by x plus y, and the question is to find x f x plus y f y. A problem where the extension of Euler's theorem can be used. Observe that without this logarithm, f would be homogeneous, but f as a logarithm of this will not be homogeneous. So what we do is, we write the same thing as e power f is equal to x power 4 plus y power 4 by x plus y. So this is now homogeneous. So let's call this left hand side e power f as a function of f. So function of f is homogeneous and the degree is 4 minus 1. So by Euler's theorem extension, x dou f by dou x plus y dou f by dou y is equal to n f of f by f dash of f. So in this case, n is 3, f of f is e power f, and the derivative of that itself is e power f. So you get the answer straight away as 3, and you can see that C is the correct option. So this is where we are using the extension of Euler's theorem to solve the problem. Let's go to the next question. In question number 16, you have u is equal to sine inverse x square y squared by x plus y, and what we require is x ux plus y uy. Again, without the sine inverse, u would be homogeneous. The degree would be 4 minus 1 3, but in the presence of sine inverse, this is no more homogeneous. So what we do is, we say sine u is equal to x square y square by x plus y is homogeneous of degree n is equal to 4 minus 1. And for convenience, this left hand side, let us call this a function of u. Therefore, x ux plus y uy is n f of u by f dash u. With n is equal to 3, f of u is equal to sine u, f dash u is equal to cos u, 3 tan u would be the answer. And the correct option is D. So these are some of the illustrations on Euler's theorem. In case you are given the higher order extended theorem, then apply that g of u into g dash u minus 1 rule, and that would solve problems of that level. Let's now go to the concept of Jacobians. So let me give you the fundamental definition of the Jacobian and a few of its properties. Normally, this Jacobian arises in the context of multiple integrals, in double and triple integrals, wherever a change of coordinate system becomes necessary for faster computations. But first, let us see if u is a function of x and y and v is another function of x and y, j is equal to dou uv by dou xy is a determinant. Dou u by dou x and dou u by dou y in the first column, dou v by dou x and dou v by dou y in the second column. So you can get this partial derivatives from the transformation equations. And for 3 variables, it becomes a 3 by 3 determinant. So what do we have about properties? We will look at 3 properties. One is j into j dash is equal to 1. That is dou uv by dou xy into dou xy by dou uv is always equal to 1, provided none of these Jacobians is 0. The second one, dou uv by dou st can be computed as dou uv by dou xy into dou xy by dou st. That is, if you are given a transformation pair between uv and xy and another transformation pair between xy and st, you can directly find out the Jacobian of uv with respect to st by a simple product of these two. Otherwise, you can actually substitute the relations between xy and st in u and directly compute, but one must make sure that that relation development does not become complex, difficult. So you can use this very selectively. And the third one is u and v are functionally dependent if the Jacobian of uv with respect to xy is 0. So there is a class of problems where the Jacobian is 0, in which case the relation between u and v can be directly established, and such a relation will not involve x and y. So in the next few problems, I will show you how we must use the knowledge of Jacobians to do some very important problems. Question number 17 gives the transformation x is equal to r cos theta, y is equal to r sin theta. The problem is to find dou r theta by dou xy. Now, if you let j is equal to dou xy by dou r theta and j dash is equal to dou r theta by dou xy, we know j into j dash is equal to 1. So according to this question, we require j dash. So j dash is equal to the reciprocal of j. So let's find out j now. J is equal to xr x theta, yr y theta. xr is dou x by dou r, and therefore you get cos theta. X theta gives you minus r sin theta. Similarly, yr would be sin theta, y theta would be r cos theta. Expand this and you will get r into cos square theta plus sin square theta. So it is r. So when j is r, j dash has to be 1 by r. So you can see the correct option for this problem is C. So this is based on a property of Jacobians. Another way of doing the same problem is to rewrite these two equations as r is a function of x and y and theta is a function of x and y, but that would definitely consume more time. So let's go to the next question. In question number 18, we have u as e power x sin y, v is equal to x plus log sin y. The problem is to find dou uv by dou xy. Well, this is a straightforward problem, but let's see what happens. So dou uv by dou xy by definition has ux uy in the first column, vx vy in the second column. Ux from this equation will be the same as e power x sin y. Uy would give us e power x cos y. Second column, vx would be 1 plus 0 of course, and then vy would be 1 by sin y into the derivative of sin y. So when you expand this determinant, you will get e to the power of x cos y minus e power x cos y. So you are getting a 0 Jacobian, which means the variables u and v are functionally related. Of course, in another question what that relationship is, for which you must know how to combine these two right hand sides in terms of u and v. And the correct option for this problem is A. In question number 19, we have the transformation x square is equal to 2y squared, v is equal to 2x square minus y squared, x is r cos theta, y is r sin theta. The problem is to find dou uv by dou r theta. If you study the first two equations, u and v are functions of x and y. If you take the next two transformations, x and y are functions of r and theta. So if you want the Jacobian of uv with respect to r and theta, let us say j, that can be the direct product of j1 and j2. So j is equal to dou uv by dou xy into dou xy by dou r theta. So let us compute. Dou u by dou x is 2x, dou u by dou y is minus 4y, dou v by dou x is 4x, dou v by dou y is minus 2y, into dou x by dou r is cos theta, dou x by dou theta is minus r sin theta, dou y by dou r is sin theta, and dou y by dou theta is r cos theta. So simple expansion of this would be minus 4xy plus 16xy. So that would be 12xy into r cos square theta plus r sin square theta, that is r. So this will be 12 into r cos theta into r sin theta into r. Now if you carefully observe, 2 cos theta sin theta becomes sin 2 theta, leaving a 6. So this should make option D the correct answer. In fact, by using x is equal to r cos theta, r sin theta directly into this system would also produce the same result. Not many times it becomes easy to do the direct substitution, but wherever the root is closed, one can think of this particular method of solving the problem. In the 20th question, we have u is equal to x plus y plus z, uv is equal to y plus z, uvw is equal to z, and the problem is to find the Jacobian dou xyz by dou uvw. Now this requires writing x, y and z in terms of uv and w. Please observe, z is directly available as uvw. So we need expressions for x and y in terms of uv and w. If you combine the first and the second transformations, you can write u is equal to x plus y plus z can be replaced with uv. So this implies x is equal to u into 1 minus v. What we now require is an expression for y. So from the second equation, uv is equal to y plus z implies y is equal to uv minus z, but z is uvw. So if you take uv common, you will get 1 minus w. So now we have an expression for x, an expression for y, and an expression for z. So let's calculate the Jacobian. J is equal to dou x by dou u would be 1 minus v. Dou x by dou v would be minus u, and dou x by dou w would be 0. Then dou y by dou u is v into 1 minus w. dou y by dou v would be u into 1 minus w, and dou y by dou w would be minus uv. Finally, dou z by dou u would be vw, dou z by dou v would be uw, and dou z by dou w would be uv. Now this is just a question of expansion, and you will get u square v as the answer, and the correct option will be found to be C. So these are some of the examples on the fundamental or the core area of partial differentiation, covering the Euler's theorem, the total derivative concept, and Jacobians. So when we meet next time, let us discuss the applications of partial differentiation towards maxima and minima of functions.